We now discuss the solution of a problem from the section Binomial Theorem and its applications. The question is related to the given binomial expansion. This question has appeared in the joint entrance examination main held on 28th June 2022 in the first shift. The given question is the number of positive integers k such that the constant term in the binomial expansion of 2x cube plus 3 by x power k whole to the power of 12 where x not equal to 0 is 2 power 8 multiplied by L where L is an odd integer is. We are given a binomial expansion, that is 2x cube plus 3 by x to the power of k whole to the power of 12 where x not equal to 0. And in this what we see is a k, and required to find the number of positive integers k such that the constant term in this binomial expansion is of the form 2 power 8 multiplied by L where L is an odd integer. So the number of positive integers k such that the constant term in this binomial expansion is of this form where L is an odd integer. We now discuss the solution of the problem in detail. We have the binomial expression 2x cube plus 3 by x to the power of k whole to the power of 12 x not equal to 0. When you expand it by means of the binomial theorem, then you will get an expansion whose general term we can write. The general term in the expansion is t r plus 1. That is r plus 1th term in the binomial expansion is 12cr multiplied by 2x cube whole to the power of r multiplied by 3 by x power k whole to the power of 12 minus r, where r takes the values 0, 1, 2 up to 12. Right. That is equal to 12cr into 2 power r, and we get x to the power of 3r is there multiplied by 3 power 12 minus r by x to the power of k into 12 minus r. And when you see the exponent of x to the power of 3r minus k times 12 minus r. To obtain the constant term, the exponent of x, that is the power, must be equal to 0. That is 3r minus k times 12 minus r is equal to 0. Then k will be 3r by 12 minus r, and where r takes the values 0, 1, 2, 3 up to 11. Why it is 11? Why not 12? We can't take 12 because 12 minus r is sitting in the denominator. We can't take r is equal to 12. R is equal to 0. Why we have avoided, I will tell you when we go into the discussion. So r is equal to 1, 2 up to 11. The constant term in that case will be 12cr into 2 power r into 3 to the power of 12 minus r, because this is x to the power of 0 is 1. Thus you get the constant term. Agreed? Right. For now the question what we are asking is, for what values of r k is a positive integer? That is, we are asking the question, k is a positive integer for what values of r? That we will discuss in the next slide. So we have for k, 3r by 12 minus r is equal to 0, 1, 2 up to 11. Now we have considered r is equal to 0 also. The constant term is written here. Now suppose you take r is equal to 0. Suppose you take r is equal to 0. Then k will be 0. But we want k as the positive integers. Therefore, r is equal to 0 is not considered. So we go to r is equal to 1. Then we apply k is equal to 3r by 12 minus r is equal to 1 is 3 by 11, which is not an integer. So leave it. And take r is equal to 2. Then k, 3 into 2 by 12 minus 2, that is 6 by 10, which is not an integer. Leave it. For r is equal to 3, we have k is equal to 3 3's are 9 by 12 minus 3, 9. That is 1, an integer. It is a positive integer. This is our candidate because we are looking for positive integers k. So now we have k is equal to 1, a positive integer, when r is equal to 3. Then what is our constant term? 12cr into 2 power r into 3 power 12 minus r is equal to 3. Substitute in this. So you will get this one, 12c3 into 2 cube into 3 power 9. 12c3 we have written down and 2 cube into 3 power 9, and we simplify. Then we get it as 2 power 5 into 3 power 9 into 11 into 5. 11 into 5 is 15, which is odd, into 3 power 9 is also odd. So L is odd, is okay, but it is not equal to 2 power 8. So we are looking for such case for which the constant term is of the form 2 power 8 into L, where L is a odd integer. That's what we are looking for. Therefore, this is not the case. So k is not our candidate. So let's get into r is equal to 4. We have k is equal to 12 by 8, which is not an integer. R is equal to 5. It is 15 by 7 k. It is not an integer. So for r is equal to 6, we have 3 6's are 18 by 12 minus 6 is 6, that is 3, which is a positive integer. Therefore, it is a candidate for us. K is equal to 3, a positive integer when r is equal to 6. And the constant term is, in this constant term, put r is equal to 6, we will get this 12c6 into 2 power 6 into 3 power 6. Now, 12c6 and all that we have written and we have simplified, and we got it as 2 power 8 into 3 power 6 into 2 power 2 into 231, which is an odd one, multiplied by 3 power 6 odd, and it is a candidate for us. So 2 power 8 into L, where L is odd, which is a candidate. Therefore, for the positive integer k is equal to 3, it is true. It is true. That is, it will be of this form. So for k is equal to 7, and it is not an integer again. When k is equal to r is equal to 8, then we have k is equal to 24 by 4, that is 6, an integer, a candidate. And let us see for the constant term. So we have k is equal to 6, a positive integer, when r is equal to 8. And so in this formula, you put k is equal to 6, k is equal to 8, r is equal to 8, r is equal to 8. In this formula, put r is equal to 8, that is 12c8, 2 power 8 into 3 power 12 minus 8, that is 4. And simplify, you will get 2 power 8 into 3 power 6 into 55, which is an odd integer. So L is an odd integer, and this is the one. Thus, for these two values, for r is equal to 6 and for r is equal to 8, we get positive integer k, for which the constant terms are of the form 2 power 8 into L, where L is an odd integer. So for the positive integers k is equal to 3 and 6, the constant term of the binomial expansion is of the form 2 power 8 into L, where L is an odd integer. So far 2 values of k we got, and still there are some more values of r. So let's look into those values of r and discuss the values of k there. We continue in the next slide. Agreed. For r is equal to 9, k gives the value 3 into 9 by 12 minus 9, 3, that is 9, a positive integer. So we are getting some answer here. So k is equal to 9, a positive integer, when r is equal to 3. When r is equal to 3, the constant term we have written, 12c9, 2 power 9, 3 cube. Simplify, we will get 2 power 11 into 3 cube into 55. This is odd integer, there is no doubt about that. But it is not of the form 2 power 8 into L. Therefore, k is not our candidate. For r is equal to 10, we have k is equal to 30 by 2, that is 15, a positive integer. Let's look for the constant term, how that will look like. For for r is equal to 10, 12c10, 2 power 10, 3 square. Simplify, we get 2 to the power of 11 into L, which is not equal to 2 power 8 into L. Therefore, this is not a candidate for us. For r is equal to 11, k is equal to 33 by 1, that is 33, which is a positive integer. So for r is equal to 11, substitute in the constant term, you will get constant term as 12c11, 2 power 11 into 3 power 1, and when you simplify, it will be 2 power 13 into 3 square, where 3 square is an odd integer, but it is not of the form 2 power 8 into L. Therefore, this k is not our candidate. So therefore, now in this slide what we have seen is 3, they are not the valid k positive integers. So what we have seen in the earlier slide, there are only 2 values of k which are positive, for which the constant term is of the form 2 power 8 into L, where L is an odd integer. For 2 positive integers, k is equal to 3, 6, the constant term of the binomial expansion is of this form 2 power 8 into L, where L is an odd integer. This we have seen in the last slide. So therefore, our answer is the number of positive integers k such that the constant term in the binomial expansion is of this form 2 power 8 into L, where L is an odd integer, is 2. So the answer for this question is to find the number of positive integers k. Therefore, the answer is 2. So that is the detailed discussion of the solution of the problem, which is based on the binomial expansion from the section Binomial Theorem and its applications. I am sure that you have understood the solution of this problem, and I wish you all the best. Thank you.